Matt, can you hear us? Matt never seems to be able to hear us. Maybe he turned it on at the beginning of the semester and just left it on, and eventually he shows up for class. Who knows? Can you hear us, Matt? Well, hopefully we'll get some kind of connection with our classmates outside of. Passcode required. In progress. Join. Okay. Well, are we finished with chapter 7?
I think so.
Chapter 8. So in chapter 8, I think actually chapter 8 should be part of chapter 7 personally. But in chapter 8, we're talking about potential energy, which we've actually already talked about a little bit. We're going to go a little bit more into detail here in chapter 8, but we've already talked about how if you lift something in a gravitational field, it requires work to do that, and you're working against the gravitational force. But once you've done that, you actually can release the object and it can fall. And as it falls, it speeds up. And that work that you did turns into kinetic energy, right? Well, as you do work on something to lift it or to lower it in a gravitational field, we call that giving it potential energy. We call it a potential energy change, essentially. And it always has to be a change in potential energy because you have to choose where your potential energy equals zero. There is no absolute zero height, for example, because it's arbitrary. And most people will just choose, the ground to be height equals zero. Problem with that is that here in North Platte, the ground is at 2,000 something feet above sea level, whatever it is. And, do we use sea level? Well, you can also use the ground at the bottom of the sea or whatever else. And this whole idea of gravitational potential energy just depends on the fact that we are near the surface of the earth, and gravity has somewhat constant near the surface of the earth that we live on, because the earth has a very we live as human beings, we live in this tiny little fraction of the Earth's atmosphere, this tiny little thing. It's like if the Earth was like a basketball and you got it wet, the thickness of the water on the outside of the basketball would be the thickness of the atmosphere that we live in as human beings, as on a regular basis. Okay, that includes if you fly in an airplane. Airplanes don't go that much higher above the surface of the earth than, I mean, they go very, very, they're still very close to the surface, so they're considering this actual, the actual size of the earth and the size of the atmosphere. So anyway, the point is that you know, if we went into space, the gravitational pull that you would feel would be very different, because you're much further away from the earth than we are normally. Anyway, we have to choose where our 0 point is going to be, and it doesn't matter where you choose it, you just got to choose it. And then we are going to measure heights above that point as positive, heights below that point as negative. That's how everybody in the world does it pretty much. So we do it that way so we can communicate with other people. And here we have a situation. Oh, Lane, you've joined us. Can you hear us, Lane?
Yep, I can hear you.
Here we have a situation with a football punter kicking the ball. Of course, before the punter kicks the ball, we can call that height where the ball is 0. And then we can say, if that height right there is 0, then the gravitational potential energy of the ball at that point will also be 0, because gravitational potential energy is mgh. So right here, mgh, height equals 0, so this equals 0. That's the potential energy, the gravitational potential energy. He does some work on the ball as he kicks it. He gives it a force for a distance, and that does some work on the ball. And so as the ball comes off of his foot, it has some kinetic energy, which is at its maximum. Kinetic energy 1/2 mv squared. So it has a maximum kinetic energy at that height. And the potential energy right now is minimum. It's 0 because we chose it to be 0 at the bottom. About halfway up, you have some potential energy and some kinetic energy. mgh for the kinetic energy, whatever this height is above that 0 point, some of its potential energy. But you also have some kinetic energy too, because the kinetic energy at the beginning is high, it's going its fastest. And up here, the kinetic energy is a little bit lower. And some of the kinetic energy from the beginning was used up, you could think of it as this thing went up higher, because it changed into potential energy. We used up the kinetic energy to get the ball higher. And so now some of that kinetic energy is in the potential energy. At the height, the highest height, there's no more kinetic energy from vertical velocity, right? Or you could think of it as kinetic energy is minimum, because the vertical velocity has become 0 and there's still some horizontal velocity, but kinetic energy is a minimum here. And a lot of that kinetic energy has gotten it to its maximum potential energy point, mgh, where the h is the biggest number that it's going to be. Then as it comes back down, the potential energy increases again, and the potential energy decreases again, and the kinetic energy increases. And then eventually it comes back, and right before he catches it, the potential energy is almost 0, because it's almost back down to that 0 point. And the kinetic energy is at its maximum right before he catches it. So you see this kind of flow between kinetic and potential energy in that situation. And here is the equation. The change in potential energy is equal to negative, excuse me, the negative of the work done by the gravitational force. If there's no work being done, just like in the previous problem with the previous example with football, if you don't consider the work being done by him kicking the ball and catching the ball, and you just consider the potential energy and the kinetic energy as it goes up and down, then the change in kinetic energy is equal to the change in potential energy. And there's a negative sign in there as well for the potential energy. That means if you add the two together, well, if you add the negative potential energy, if you add this to both sides, you get kinetic energy plus change in kinetic energy plus change in potential energy has to equal 0. It's a nice conservation equation for you. You know, they're going to use this for a particle that's going to move along, but now they're going to give our force, they're going to make the force into a function of x. So we're going to have to do some calculation, of course, with some calculus. We have to calculate the work done. They want to know the difference in the potential energy that moves from one point to another. So we're going to essentially calculate the work in this problem, because in this equation right here, if you know the work, then you can actually take the negative and that has to equal the change in potential energy. So that's what they're going to do in this problem. They're going to calculate the work and set it equal to negative change in potential energy. So here we are calculating the work, doing that integral from our first point to our second point, so on, 7 joules. And then that work has to equal the negative of the potential energy change. So the potential energy at point 0, they're using their potential energy function by doing the indefinite integral. If you do the indefinite integral of the work, you get a function for the potential energy. So the indefinite integral without plugging in the numbers is this. And they use that to calculate the potential energy at the beginning and the potential energy at the end, and then they set them equal to each other, and it turns out that it's true, so it works out just fine.
I've never heard the phrase indefinite integral.
An indefinite integral means that you're not using the limits of the integral to calculate a number.
It's just infinite.
It's not infinite. It just means you're not completing the integral. It means that you're not evaluating the integral. So to evaluate something, you have to give it a value. You have to plug in numbers. This integral is only done symbolically, I guess you could say. And it's not infinite. You're just, what you're doing is you're creating a new function that represents what that integral is, right? So when you do the definite integral, when you do the definite integral, you actually plug in these numbers at the limits of the integral, right? And then when you do that, you're actually going to evaluate this function that comes out of it. This is the function that comes out is 1/3 times 3 times x cubed, right? That's goofed up. What's wrong? Yeah, no, that's right. That's still right. Because a is equal to 3, right? This problem. Yeah, a is equal to 3. So 1/3 times 3, which is just 1, right? And then x cubed. So the indefinite part is this part before you actually plug in these numbers. But you also have to add a constant to it when there's an indefinite part. You're going to add in the initial value of u. So what you do is you figure out the initial value of u, plug that in for your constant. You plug in a 3 for your a, and you get the indefinite integral. The value of the indefinite integral ends up being x cubed plus 0.5. And then you can plug in whatever you want to calculate the potential energy. Does that make sense? All right, so when you have multiple particles, then of course you're just going to have to calculate either all of that stuff for each particle independently, or if you have multiple particles that are connected to each other somehow in some kind of continuous manner, then you're going to have to do it over the entire. You're going to have to integrate over like some kind of volume, which we don't do in this class. So it's not a big deal. But anyway, the point is that in the end, we get this equation, which is the potential energy. And this comes from that previous example here. The potential energy is equal to the mass of the object times gravity times the height of the object, or the relative height of the object. And they're saying this is near the Earth's surface, which is true because little g is only valid near the Earth's surface. And then you add the constant, where the constant is the potential energy, the initial potential energy of the system, essentially. So, or the potential energy of the system at its lowest point. No, not its lowest point, at its starting point. Is a better way to say that. So here we have a hiker that's going to the summit of this place, 147 meters. 75 kilogram hiker. What's the gravitational potential of the hiker Earth system? So they draw this picture here. Here's the base of this hill, here's the top of this hill. And we're measuring from the base to the top. So our height is going to be one, or our Y, our difference in height is going to be 147 meters. And the potential energy at the base, which we're going to call our potential, our initial potential energy, is going to equal 0, because that's going to be height 0. Potential energy of the summit is going to be mgh at the summit, 108 kilojoules when you plug in 147 newtons and the mass, and g. And at sea level, you actually get a potential energy that is measured with a height of negative 48 meters. So the potential energy at sea level actually is a negative potential energy. You say, well, how can energy be negative? It's just potential energy is negative. Remember that potential energy is relative to a point that you choose, so you can definitely get negatives for that. All that means is that if you start off at your 0 point for potential energy and you go to a negative potential energy, that means you're going downhill. That's really all it means, right? It means that it means to get to that place, you actually are going to gain energy rather than lose energy in some other way, rather than potential. Right? When you go uphill, you're trading off your kinetic energy to get up the hill, for example, or somebody has to push you up the hill. They have to give you that energy to get up the hill. But if you're going down the hill, you're actually going to gain some other kind of energy, like you roll downhill and you're going to gain kinetic energy, right? Or somebody has to slow you down with using work because you're trying as you're going down. So that's what that negative potential energy amounts to. Now, there are other types of potential energy. Elastic potential energy from stretching things or compressing things. When you stretch a rubber band, it wants to go back to where it was before. So it's like you're storing energy in the elastic property of the rubber band. And that comes from the work done on the rubber band to stretch it, or the work done to compress something that will bounce back to where it was. And this is elastic potential energy. And that work is done by the elastic force, which we've dealt with before. The elastic force, remember, has to do with Hooke's law. It's K times X. And if you calculate the work done to stretch something, you have to do an integral over K times X, right? And it ends up being 1/2 kx squared, which we've also already done. And so the difference in the work is 1/2 kx final minus 1/2 kx initial. So wherever the rubber band starts at, wherever the rubber band ends at, then you take the difference of the work for those two different stretches, you can think of it as. So this becomes the elastic potential energy. Elastic potential energy is 1/2 kx squared plus a constant, where the constant is its potential, the potential energy in the rubber band at its original stretch, at its original position. And most people just say that it's 0 again. They say, well, we're just going to assume that before we stretch it, it's going to be a 0 potential energy stored in the elastic object. And after we stretch it, we'll measure from that original position to there to get that final potential energy. Usually we actually say that unstretched, that initial position is when it's not stretched at all. When the rubber band or the spring or whatever it is we're stretching is at its unstretched length, or its relaxed length, as we actually often call it. We're just saying that that's 0, so that if you take it from its relaxed position, stretch it outward or compress it inward, then you measure the distance from the relaxed point to whatever you stretch it to. So here we have a spring that is, its unstretched length is 20 centimeters, and it has a spring constant, K equals 4 newtons per centimeter. And we want to know how much elastic potential energy the spring has when you stretch it to 23 centimeters, or how much of it's stretched to 26 centimeters, or how much more if it's 20, if it's gone to 26. So potential energy in the spring again is 1/2 kx squared, where the initial is 0, it just becomes 1/2 kx squared. And so you just plug in the numbers, right? 0.8, 0.18 joules. And remember the 3 centimeters is the 3 centimeters, you would have to convert it if the K was given in meters, but the K in this case was given in centimeters, at 4 newtons per centimeter. So the 3 centimeters you can leave in there, you don't have to convert it. And it leaves you as 0.18 joules for the first stretch. And the second stretch, when it's 26 centimeters, when you measure it, is actually they're actually only going to count the last 6 centimeters. So the 6 centimeters from, they're essentially going to take the, no, they're not doing that. Okay, so that's good, because I was thinking if they're doing that, they're wrong. They're actually doing this correctly, which I wasn't sure that they were doing it correctly, but now I am. So what they did is they took, so here's your unstretched spring. And it has this unstretched length of 20 centimeters. And then they stretched it out. So this is where x equals 0 right here. This is x equals 0 when this thing is not stretched out, right? Then they stretched it out to 23 centimeters long. So if the original unstretched length is 20, actually, that's not right. Yeah, that's right. So that if they stretch it out to 23 inches, then 23 centimeters, then it's coming out to here, this distance. And this change here is only 3 centimeters. If they go out to 26, then it's 3 more, right? What you don't want to do is you don't want to say, you don't want to use the 23 centimeters in your equation to calculate this. You want to use 3 centimeters. You want to take the unstretched length, subtract the stretched length, and that will give you how much it has been stretched, right? So that gives us the first one. And then they did the same thing for the second one. They took 26 centimeters, subtract 20 centimeters, and they got 6 centimeters of stretch for the second one. And then they took the difference, which gives you a 0.54 joule increase. So if you go twice, if you stretch this twice as far, you don't get twice as much energy, you get 4 times as much energy because of the x squared thing in there, right? So that's elastic potential energy. It's just a different kind of potential energy that's stored inside the spring instead of stored inside the gravitational force. Yes?
Why do you multiply it by the difference in the stretch length and maximum length instead of just the stretch length?
You do the difference between the stretch length and the relaxed length, because Hooke's law, you have to choose your 0 point, and we chose our 0 point to be at the relaxed length.
Okay, and the relaxed length in that is
20. Yep.
The strength is 5. Thank you. Sorry.
So that's always true for potential energy. Potential energy, you choose your 0 point and then you measure from there. Most people, when we do elastic stuff, most people will measure from the relaxed length just because just makes sense. So, all right. So, what if you have both gravitational energy and elastic potential energy? For example, you have a spring that has a mass hanging from it. So the spring itself is storing potential energy, and there's gravitational potential energy involved as well. So if our relaxed length is right here, we'll call that y equals 0. And then you put the mass on it, and the mass stretches it out, right? When the mass stretches out the spring, it actually puts potential energy into the spring, but the mass is going down in a gravitational field. So when you're going down in a gravitational field, you're also getting some potential energy from gravity. There's a gravitational potential energy involved, right? In that situation. So you have to add together your potential energies. there's multiple potential energies involved, right? So in this case, you have the zero kinetic energy involved, really, and you have on either side, because we're not moving in this case, but on the right side, so before when the mass is up at the top, you have zero kinetic energy and zero potential energy. But on part in the second position, you have zero kinetic energy, but you have gravitational potential energy and spring potential energy that you have to add together for a total energy. And you can actually solve that equation to find out how far that goes. That essentially gives you the equilibrium point between gravity pulling it one direction and the spring pulling it the other direction. Tells you how long the spring will stretch out. Which is a good thing to know if you're a bungee jumper, right? If you're a bungee jumper, it's a really good thing to know how far that spring is going to stretch, because you don't want it to stretch longer than the thing you jump off of is high. It would be unfortunate. And that is actually the equation that they use for that. They know the spring constant of their spring, and they know the length of their spring.
So kind of not important, but for all intents and purposes, in physics, when we talk about springs and elastic like rubber bands, can we just use Hooke's law for both of those?
Yeah, Hooke's law works for materials when you stretch them to a point where they will spring back to their original shape and size, right? If you stretch something to the point that it won't spring back, where it gets permanently stretched out, or you compress something where it's permanently compressed, then Hooke's law doesn't work very well. It works a little bit, but not really well. If you stretch it to the point that it breaks, then it definitely doesn't work. But yeah, so yeah, for sure. So here they actually do that problem, and they use that formula to calculate what length the spring will stretch out to, and they calculate the potential energies and so on and so forth. It's just plugging numbers in. It's not very difficult for that formula. However, what is interesting about that problem is that you can actually use those potential energies to calculate kinetic energies as well, because as a spring, so if you put a mass on a spring like that and you let it go, it actually speeds up as it goes down, and then it slows down, and then it speeds up again. It goes back and forth because the spring is pulling it up, gravity is pulling it down. It becomes an oscillator essentially, right? Well, the kinetic energy while it's moving is coming from the spring potential energy and the gravitational potential energy, right? As the spring goes down, as it falls down, the spring is going to slow it down and gravity is trying to speed it up. But when those two forces essentially meet their equilibrium, that's when it stops and it turns around and the spring pulls it up as gravity tries to pull it down. Because the spring force gets stronger and stronger and stronger the more you stretch it. So eventually the spring force becomes equal to the gravitational force and it stops the object, right? But then it turns it around and the spring pulls it backwards, right? And so on. So that's where you get that oscillation from. So you can also calculate the potential, the spring energy. I mean, sorry, the kinetic energy, and calculate the velocity from that. So anyway, energy. Energy is associated with things in the universe. The Big Bang, 10 to the 68. It's a big number.
Kind of interesting statement. So just say, all right, Big Bang.
How do you think they
This
calculate?
is how much energy is released. I would assume
That's not how much energy it released. That's how much energy was in it.
And I would assume that they found that through the movement of all the planets away from the direction of the Big Bang.
So yeah, they've essentially observed the universe, and from their observed observations of the universe, they can get an approximation, a very rough approximation, but an approximation of how much energy is in the universe today. And the amount of energy in the universe today, kinetic energy, potential energy, also that includes mass, because mass is actually kind of like energy because of E equals mc squared, right? All of the mass in the universe was created from the energy in the Big Bang. So, so they take all the kinetic energies, all the nuclear, energies in the stars, all the chemical energies and nuclear energies in the planets, and they kind of give a rough approximation of how much energy in the universe today, and that's how much energy must have been in the Big Bang, right? So yeah, annual world energy use 10 to the 20. You think, oh, that's not much smaller than the Big Bang. Yes, it is. It's much smaller. That's a 10 to the 68 and a 10 to the 20, right? 10 to the 20 is not even a fraction of a millionth of a gazillionth of a percentage of 10 to the 68. It's
Well,
just,
yeah, a million seconds versus a billion seconds. Like a million seconds is like 11 days, and a billion seconds is like 30 years.
yeah, that's only 10 to the, that's 10 to the 9 versus 10 to the 6, right?
Exactly, and it just gets so much more between.
Yeah, it's
different,
insane.
Here.
And so the interesting thing is the large fusion bomb is only about 10,000 times smaller than the energy we use every year, right? So the bomb that we dropped on Hiroshima is 1,000 times smaller than that. Metric ton of dynamite, a gallon of gasoline. A metric ton of dynamite and a gallon of gasoline are only 10 times difference-ish. 40 times difference. A gallon of gasoline has a lot of energy. And this is, what's that?
I said just drink a little bit of gasoline.
Well,
For the rest of your life.
yeah, so gasoline has an incredible amount of energy in it. And that's why we use it for cars. And you compare it to the amount of energy in a battery, for example, that's used in the car. A battery that has the same weight as a gallon of gasoline would not even start your electric car. Like it would turn on the car and you'd roll forward a couple inches and then it would die. It doesn't have nearly the amount of energy as a gallon of gasoline. Gallon of gasoline weighs about 6 pounds or something like this, 8 pounds. I don't know what it is exactly. Not very much. An 8-pound battery. You can't run an electric car off that.
That's less
At
than
all.
this probably.
It's the size of your laptop. The battery in an electric car is 1,000 kilograms. It's essentially a metric ton of battery. And it'll only take you about a couple hundred miles in the best electric cars today. If you have a metric ton of gasoline, you know how far you can drive with that much gasoline? You can drive around the entire United States, like the outside circumference of it with that much gasoline. Probably, you can probably even go around Alaska as well, or go to Alaska and back. That's a lot of energy in gasoline. Incredible amount. So anyway, here's the amount of energy required to break a single DNA strand. 10 to the minus 19. Doesn't take much to break a DNA strand. Breaking DNA is what your body does to replicate itself. It has to break apart a DNA strand. Breaking a DNA strand is what nature does to you when you get a sunburn, and it's the amount of energy required to cause cancer. That's all it takes if you're unlucky enough. Usually it takes a lot more than that for most people, but anyway, that's energy for you. So conservative and non-conservative forces. When we talk about a conservation in physics, we're talking about a quantity, a thing that can be measured in the physical world that never goes away. It just gets traded back and forth. It just gets moved around. Energy is one of those things in many situations. Not in general. In general, energy is not conserved. but in many situations it is. And when it is conserved, we call situations like that, we call the forces in situations like that conservative forces. So in the situation where you have gravitational potential energy and you have elastic potential energy and you have kinetic energies, but you don't have anything that turns your energy into sound or heat or deformation of an object, like bending, stretching, breaking, where there's nothing like that going on, then it's considered a conservative system, because heat, you can't turn heat back into something else very easily. If you heat something up by using friction, the heat immediately radiates away, it escapes and leaves the system, and it wanders off into the universe. In fact, every time we make heat, a certain amount of it literally just kind of walks away. It goes off into the universe and never comes back. That happens a lot in the universe with the energy. It's the leading cause of energy loss in the universe. Light is another thing that kind of just wanders off into the universe often and just kind of never gets turned into any other kind of energy. Sound wanders off into the universe. Energy does this all the time, and this is why stars die, for example. Stars die because they're creating all this heat and all this light, and this stuff just kind of wanders away from the star. And when this stuff wanders away from the star, it's wandering away with mass. It's attached to mass. It's attached to other things. I mean, and these things just leave the star, and the star gets less and less massive, less and less energetic, and eventually it dies. And believe it or not, eventually the universe will do that too. Eventually, all the things happening in the universe that have energy going on, they have heat leaving them, they have light leaving them, they have sound leaving them. All these things that are difficult to kind of contain, they just kind of wander off in the universe and do their own thing randomly. But eventually that energy is not organized enough to do anything with, right? There's not really a machine or a device out there where you can just gather up heat that's being released from humans, for example, and just gather up that heat and turn it back into like energy that you can use in your car, or energy that you can use to build something, or energy that you can store in a battery. It's very difficult. You can do it somewhat. There are devices that can capture heat and turn it back into electricity, but they're very inefficient. You can only capture a small percentage of the heat that's around us. And even the process of it is pretty inefficient. So when those things are present, when friction and sound and light are present in a system, then that system usually isn't conservative. But if you can have a system that doesn't include those things, that's not creating those kinds of energies, then you can have a fairly conservative system. So a mass on a spring, if you have a pretty good spring that doesn't create a lot of heat, because stretching of springs does create heat a little bit, and if you have no air resistance, so you have no drag forces, no friction forces, you can actually have a pretty conservative system of a mass bouncing up and down on a spring. And that system will be conservative. The energy that is stored in the gravitational potential energy will become kinetic energy as it falls downward. And then as the spring expands, it will gain potential energy in the spring, enough eventually to stop that from going downwards, and then it'll pull it back upwards, and it'll just go up and down and up and down and up and down forever if you don't lose any energy in any other way, if no energy leaves the system. Of course, we've all seen this kind of experiment or done this kind of experiment, and it never works out that way. It goes for a while, and then it eventually, peters out and dies. And that's because of those non-conservative forces. So conservative forces would be things like the gravitation. The gravitational force is a fairly conservative force. The spring force is a fairly conservative force. And the frictional force is not. It's a non-conservative force. Drag forces are non-conservative forces. When you get down to the very small level in physics like atoms and particles, subatomic particles, even in some cases, things like molecules. At those levels, things are very conservative because friction means almost nothing to those things. They're smaller than the objects that create friction. So at an atomic level, when atoms bounce off of each other, for example, it's pretty much perfectly elastic because there is no friction. But it's not always perfectly elastic because oftentimes they create light. Oftentimes when you have subatomic interactions and atomic interactions and even molecular interactions, you have light created. And sometimes there's heat created in a different way. And so not always are those things elastic, not always those things perfectly conservative, but sometimes they can be, oftentimes in fact. And the same thing goes for things on a very large scale. So planets orbiting around each other, for example. Planets orbiting around each other are so far away from each other that there's no friction involved in that situation. There's no heat being created or light being created. And so that situation is very conservative. This is why the Earth has been rotating around the sun for 5 billion years, because the energies are being conserved extremely well. And they will continue to do this for many more billions of years, very likely. So, very large interactions and very small interactions tend to be much more conservative. Now, if you have a very large interaction of like a planet hitting another planet, that's not going to be very conservative. It's going to create a lot of breakage. It's going to create a lot of sound. It's going to create a lot of light. It's going to create a lot of heat. And there's going to be a lot of energy that's going to leave that interaction and just kind of wander off in the universe again. In a non-conservative way. Mathematically, a conservative interaction or a conservative force is independent of the path that it takes. It doesn't matter how you get from point A to point B. It just matters that you go from point A to point B. And why doesn't it matter? Why does the path not matter? Well, because if there's no friction, the path doesn't matter because the path is the thing that friction depends on, right? Longer paths mean more friction. Shorter paths mean less friction, right? But if you have no friction, the path doesn't matter because the only energy you lose, or the only energy that is kind of messed up along the path is friction, right? What does that mean to us practically speaking? What that means to us practically speaking is that if you're going down a hill, for example, if you have a ball that's going down a hill, if the hill has no friction to it, it wouldn't matter if you did this to go down the hill from top to bottom, or if you went down the hill like this, straight down, kind of more straight down, or if you went down below the bottom of the hill and came back up. It wouldn't matter. In none of these the paths doesn't affect the beginning and ending result. At the beginning, if you have an initial velocity, and at the end, if you have a final velocity, that gives you an initial kinetic energy and a final kinetic energies. Your initial and final kinetic energies will be the same. And your initial total energies will be the same. Initial potential energies will be the same. Final potential energies will be the same. Everything will be the same, beginning and end, no matter what happened in between. And that's what they mean by the path doesn't matter for conservative forces, because the friction isn't there to make it a difference, right? So conservative forces are path independent. The path doesn't matter. And for conservative forces, if you have a closed path, which means if you end at the place that you begin, so if you go down the hill and then you come back up to the top of the hill, the total amount of work done is going to be zero. The work done by gravity on the way down is going to be some amount. Let's say that gravity does 10 joules of work to get you down the hill. And then you end up back at the top of the hill. Gravity does negative 10 joules of work as you go up to the top of the hill. It slows you down to your original velocity at the top of the hill. And the sum of those two works, 10 plus negative 10 is zero. And you're back to where you started. Your energy is back to where your kinetic energy is back to where you started at the top. Right? No change in total energy when you have a closed path system or a conservative system. This is the idea behind machines. Machines are usually designed to be a closed path machine, where you start at some point in energy, you go through some process and you get back to that same point, and then you go through it again and you get back to that same point. But all machines have an efficiency of less than 1, which means their closed path integral of the work is never 0. That you always have to put some energy into the machine to make it go through that path and get back to where it started. So a toaster, for example. A toaster is a machine that starts with a piece of bread in it, right? You put a piece of bread in it, you heat it up, you turn the bread into toast, and you eject the bread out, and then you get a machine that's cold again. And then if you want to make toast again, you have to heat up the machine, put the bread in, toast the bread, eject the toast out, and then it cools down and it's cold again, right? You have to put the electricity in there. You have to put the bread in there. Those are things that we have to put into the machine. That's energy we have to inject into the machine. And that makes it less efficient. It's not just a machine that works on its own, right? It doesn't just, the bread doesn't just magically appear there, and the toast and the energy, the electricity doesn't just magically go in there, right? We always have to be putting stuff into the machine to make it go through its cycle, right? If you talk about a car engine, we have to put in gasoline into the car, and we have to light it on fire, and it turns the engine, and some stuff comes out. There's different things that come out, like carbon dioxide and water and carbon monoxide and other things. And that stuff comes out of the machine, but it doesn't go back. You can't turn all that stuff that comes out back into gasoline and put it back in the machine. Actually, you can, but it would take energy to do that. A lot of energy. And so you have to use more energy to make more gasoline, put it back in the machine. So we're constantly putting energy into our cars to make them go. If you had a machine that was a closed path work equals 0 machine, then you would burn your gasoline, it would come out the other end, come out the tailpipe, and you just put the tailpipe, you connect the tailpipe to the gas tank. Your gas tank would just burn the fuel again. That would be a closed path car, and that would be great, right? If you can do that. Now, the funny thing is that there are always people out there that are claiming that they've created a machine like this that can do this. And it is absolutely impossible according to the laws of physics that we have discovered. You cannot have a machine that does not require you to put energy in. They call them perpetual motion machines. Machines that you start up once and they just keep going forever. And you never have to put energy in. Every single machine that you see like that on YouTube or in other place, and there are lots of them out there, are farces. There's something in them that they've put in there that is keeping the machine going that you can't see. And it's a lie. Usually it's something magnetic. The magnetic or electromagnetic. Those are the easiest ways to fool people's eyes. And I have had several calls while I've been a teacher here, from people that have invented they call them a zero energy machine, or free energy machines, and they want me to validate their free energy machine so they can get a patent on it, And it's hard to deal with people like that, because immediately that they're wrong, and you don't want to meet with them to tell them why their machine is wrong, because they get angry. And so I just tell them from the front, you're wrong. That's the first thing I tell them. It's impossible. You're wrong. You're done. We're done here. I don't meet with them. I don't talk about their machine. I don't see their machine, because it's never been done and it never will be done. Yes.
So I'm sure you've heard about it, and I know I'm pretty sure you can't get energy from it. It's one of the perpetual motion ones. The wheel with marbles on it. You know what I'm talking about?
Yep. There's several versions of that one.
Isn't the motion from that generated by gravity?
So gravity is a conservative force, right? But the problem is that friction is not. So they have when there's things like the marbles, usually the trick is that they use an electromagnet, and they usually use an electric magnet and a magnetic marble. So the marbles are usually made of steel, and then some tricky people use glass marbles, and one of the marbles is painted to look like glass, but it's actually, or it's got some kind of magnet embedded in it. And then the machine somewhere usually has a platform. Inside that platform is usually a battery with an electromagnet. And that battery it detects when the marbles come down, and it turns on and it propels that one electromagnet, that one magnetic ball, and pushes it around the machine. I built a machine similar to that when I was in college. That's kind of a fun machine. It's essentially a marble track. It's like a racetrack for marbles, where the marbles race down in gravity. You put them in and they go back and forth on these little zigzaggy things. And it's made of aluminum. So it's just an aluminum plate with these things machined into it. And on one of the tracks, you put a regular ball bearing made of steel. On the other one, you put a magnet. It's a ball magnet. Well, as the magnet rotates, it actually creates a current in the aluminum. And the current in the aluminum creates an opposing magnetic field to the magnet. So while the ball bearing, that's a regular ball bearing, goes boop, 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 back and forth really quickly, the other one goes boop, boop, really slowly. And it's really trippy because you're like, they look exactly the same, but they're nothing the same, right? And that is the exact opposite of what they do. And that's one of the reasons none of those machines are made of metal. They're almost always made of wood or plastic, because if you're making them of metal, that marble in there that's a magnet will interact with the metal, even if it's not a non-metallic, a non-magnetic metal like aluminum. It still creates a current in it, which creates an opposing magnetic field, which slows down that marble. So yeah, it's interesting, these machines, and you get used to them as a physicist and an engineer, because as an engineer, if you become professional engineer someday or scientist someday, you will encounter people like this. They will seek you out. It just happens. It's all kinds of people seek you out.
Do you know them from like, were they students?
No, just random people. They get online and they look you up and they say, oh, this is somebody I can trick. And sometimes they don't even know that they've been tricked, and they're like peddling. They like bought this from somebody. That happens often. I paid $1,000 for this, and it's going to make us all rich. Well,
I've seen YouTube videos about this guy trying to explain how he thinks magnets can solve the energy crisis.
Yeah,
And it's just like,
well, magnets already did solve the energy crisis. They're called generators.
that's true. Like, I don't know. He just made it. He tried to say that somehow magnets can be used for cold fusion, and it's like,
yeah, there's a lot of goofy things out there. The problem with it is that people think they understand science, but they've never actually studied science. To understand science, you have to do the experiments. You have to understand the math. So, all right, you guys have a good weekend. We will see you later.
yep.
We will get
Have a good
back to the
weekend.
rest of this on Monday. We didn't quite get it done, so we'll extend this off till Monday. See you later.